Thank you for joining us for a very interesting session on CCUS technologies and engineering. My name is Emil Thomas. I'm a director with EY's Energy Transition Wing, and we work with a lot of these companies on some of these initiatives in the carbon capture space. Every day, the world is sort of emitting over 100 million tons of CO2. So, I think this is an opportune moment for us to discuss the different technologies, especially from a cost and engineering perspective, given that India has set its net zero goals for 2070 and the amount of industrial decarbonization that's needed to achieve those goals. Looking at carbon capture and the different technologies that enable that is quite an opportune thing, right? So the first speaker for today is Smitha Rao, who's a carbon capture specialist from ABB, and she's going to be talking to us about the buzzword of the year, sort of AI, and how automation and AI is going to help us achieve our carbon capture goals. So over to you, Smitha.
Good morning. I hope I'm audible. So I'm very excited here to be talking about how we can transform one of the climate challenges, CO2 emissions, into something, valuable opportunity through AI and automation. Before I move on, I would like to mention Mr. Joy Rajashri Banerjee, who is my co-author in this. Yeah, so in the next 15 minutes, I would like to talk about three things. Why carbon capture matters now, how ABB makes it work, and what results you may expect. So for 2,500 years, human beings have been consuming Earth's resource in a one-way direction: take, use, and dispose. Earth's atmospheric CO2 is at a high of 420 ppm. That's 50% more than pre-industrial levels. We emit about 38 gigatons annually, whereas our capture rate is just 0.05 gigatons. That's less than 2%. AI data centers, they are the biggest energy consumers of today. Annually, our emission is 38 gigatons, like I mentioned, and we need to capture about 5 to 10 gigatons in order to meet our climate goals. That is 100x more than today's capture rate. So traditional mitigations won't suffice anymore. This is just like bailing out a bathtub of water with a teaspoon while your faucet is running full blast. So this is not just environmental crisis anymore. It is business imperative. The carbon taxes are rising and regulations are tightening. So what's the solution, you ask? Well, that's where carbon capture and utilization comes into play. 70% of the captured carbon in today's day and age goes into enhanced oil recovery. About 29% goes to long-term storage. 1% or even lower gets converted into useful products. So now where's the opportunity? Do you spot that? Yes, that 1%. We have an opportunity to change that number. Here's a fundamental shift. Carbon dioxide is not a waste. It is a resource that's available abundant, and it's only waiting for it to be used in the right way. CCU benefits by displacing high emission products with alternate carbon products. Okay, so let me just show you how it works. Like any technology, carbon capture and utilization has its own challenge. And let's be honest about both. While carbon capture and utilization helps in economic growth by bringing about jobs and reduces emissions with low carbon alternatives, and promotes business circularity, it also has its cons, like high initial costs, infrastructure requirement, technology challenges, regulatory hurdles, and so on. So this is where technology comes into play. It can help us bridge that gap. While the benefits outweigh the barriers, we still need the technology for us to bridge that gap. Okay, this is where it gets exciting, and this is where I want to stress upon in today's topic. Technology is an enabler for us to make CCU viable. Research shows that with these technologies that you see in the board, you can achieve up to 8% reduction by 2030 in the GHG emissions. And this is just for one sector, that's energy sector. And by 2050, you can achieve up to 20%. Now, these technologies, I'm not talking about far off in the future. They exist today. And as we move on, you'll see which are those technologies. Okay, this is where rubber meets the road. So just imagine an e-methanol plant, where technology completely orchestrates every move, monitoring real time, learning from insights, and also ensuring the performance and energy reduction. All unified while you obtain 10% energy cost. I'm not talking about a science fiction here. I'm talking about what ABB is delivering today in real life scenario in the CCU projects. Let me show how this works. So ABB commitment towards CCU is that it provides end-to-end automation solution in the CCU projects worldwide. Our comprehensive technology range from electrical systems, automation platforms, assets and safety management, integrated solution, not just point products. So we have proven track record, and we are in this business for over 100 years. So I would like to talk about 3 key ABB solutions that has helped us achieve the benefits that I've just spoke about in the CCU projects worldwide. The first solution is ABB Ability System 800XA. This is the brain of your CCU operation. This is not just another control system that I'm talking about. Think of smartphone versus your old flip phone. Same functionality, but completely different capabilities. And that's what this is. It is a multifunctional automation platform integrating process controls, electrical systems, safety, telecom, asset management, everything unified in an environment. It brings about seamless coordination between your physical, electrical, and chemical systems. Now, you don't need to start everything at once. You don't need to build it all at once and say, okay, I'm going to implement it later. No. So it enables modular expansion as your carbon capture utilization facility is growing. The next one that I want to talk about is the Optimax. Now, this solution has some key features. You remember in a couple of slides back, I mentioned about 10% energy cost reduction. And this is the solution that makes it work. So this is a digital energy management system for microgrids and industrial sites. CO2 reduction, energy cost savings, and optimal energy flow across your entire CO2. So which of these is important for you? The good news is you get all of this in this solution. So it reduces CO2 emission without compromising your operational efficiency. It ensures that the right energy is selected based on its availability and cost. This is just like your energy advisor that's similar to your financial advisor, which helps you select the best, abundant, and the cheap availability and helps you make that decision. Just imagine your CCU plant completely making or adjusting its operation based on the renewable energy when abundant of solar or wind is available with reduced cost. And that's what this is capable of, completely doing that for your entire operation. The third solution that I want to talk about is Sensite Plus. Now, this one is your purity and safety guardian. You can't manage what you can't measure. And in CCU operation, purity and safety is everything. So this particular solution, it predicts or detects your impurities in your pipelines, in your gas flow, like hydrogen sulfide and water. It ensures process integrity, protects your downstream equipment, your pipelines, like I mentioned. It also makes, provides insights for you so that you will be able to make informed decisions. In today's day and age, safety is just not about people. It's also about business continuity. And that, right now, I gave you a couple of informations and you would be wondering, what next? Where do we go from here? And that's where I wanted to emphasize on these points. The focus on CCU, carbon capture and utilization, has only picked up. The momentum is accelerating, and there's no going back from here. These solutions, or the future solutions, have to be digital and AI native. Primitive way will not help if you want to achieve economic efficiency and energy security. The last one is the technology that I spoke about is not future. They are more relevant today than ever before. So let's work not just on preserving, but also improving the environment that we live in. That brings me to the end of my topic today, but I wanted to integrate three big imperatives and leave you with that. One thing is stabilizing atmospheric CO2 is very important. I'm not telling, completely remove it and make it zero. I'm saying we need to be at a place where it was to have a meaningful life. Another one is adopting circular carbon practices so that we can use carbon dioxide in a more meaningful way and a more, viable economic products. So for a country like India, this is not just environment, it is strategic, because India's import of fossil fuel is almost about 85%, and we need energy security and energy self-sufficiency. The last one that I want to tell you is you don't need to start everything, but if you want to advance in CCUS, you can concentrate on pilot projects, feasibility studies, and ABB is here to support your journey in that. Okay, so thank you for your time and attention. Remember that CO2 is not a challenge. It depends on how we see it. It's an opportunity that's waiting for us to utilize it. Thank you.
Thank you, Smitha, for that. I think we'll leave questions at the end. Our next speaker is Mr. Deepender Bora, who's a geologist at Schlumberger. He's going to talk to us about his global experience on carbon sites and how they're being screened. Deepender, over to you.
Good afternoon, delegates, and thank you, India Energy Week Organization Committee, to give us an opportunity to talk about a technology that I'm going to brief in next 15 minutes. So, while it is published and grossly known, the overall carbon storage potential of sedimentary basins in India, there is a lot of room to improve it through numerical simulations. So that's what I'm going to present today. Our conventional technology is changed or is improved to handle the simulations of carbon dioxide in the saline aquifers. What I'm going to talk about is basically the conventional petroleum system modeling tool, the technology called Petromod, and how the regional basin models can be significantly improved to simulate carbon capture or storage potential and screening of the sites at the basin scale. Different subsurface avenues where the carbon can be injected. What I am going to talk is primarily on the saline aquifer today. Then there are other options like depleted oil and gas reservoirs or the CBM, which requires special treatment. So if you look at from your left to first three figures, regional scale modeling, and the first two figures is what I'm going to talk about. That's about how to use existing basin models to exactly simulate hydrocarbon storage and find sweet spots for injection. Where the remaining three, where you see the static model, dynamic model, and advanced geomechanics, this is when real injection starts or the project is implemented. So the first two are what I'm going to talk about. So what we are interested in is actually for the target reservoir, for the target saline aquifer reservoir, suitability and storage. These are the two factors we focus on. Suitability means what are the best areas where it's suitable to inject. So what we need is basically temperature, pressure, sealing capacity of the overlying rock, of the aquifer, and then salinity and stresses of the rock. These all are, those who are familiar with the basin scale modeling, these are the typical byproducts anyway comes in. The second part which is added is storage capacity. How much carbon can really be injected in those sweet spots through modeling, carbon dioxide trapping mechanism, modeling free and dissolved phase in water, and also the concentration and precipitation as well, carbon dioxide, the secondary mineral precipitation in the reservoir. So these are the model. Now the workflow, those who are familiar with the conventional petroleum system modeling tools, this tool is used to model hydrocarbon generation, migration and accumulation. Now the added to the same technology is, rather than generating hydrocarbon, we are injecting, we are putting the dummy wells and injecting carbon dioxide and simulating same migration of the carbon dioxide instead of hydrocarbon. So same technology but added for the simulation of carbon dioxide. Now, so what we need is basically, what we are trying to address is pressure, temperature of the saline aquifer through modeling, rock properties, porosities and permeabilities, top seal capacity, how much bigger column of carbon dioxide can it hold, and what trapping mechanism works in which part of the basin based on numerical simulations. And then free phase versus dissolved phase, quantification of that, and then distribution of carbon dioxide as well as the water phase. And adsorption of the carbon in the core is not part of this talk today. And then mass balance at the basin scale, how is the mass balance injected versus stored. So this slide is just for those who know basin modeling, to build a model at the basin scale, to build a model for the reservoir aquifer reservoir, where we try to inject the hydrocarbon. Then this is again, I'm skipping, it's temperature simulation. Those who are aware of the basin modeling, is simulating the temperature for the aquifer, because CO2 storage is dependent on PVD properties of the CO2, temperature, pressure, porosity, permeability. So this is a simulation output. Then the migration we are doing through full physics Darcy simulation. So Darcy simulation is taking into consideration buoyancy, capillary pressure and overpressure. That's how the CO2 is migrated. So that's what I meant. While overall the gross numbers are known, but they are based on basic calculations of NTG, porosity, saturation, and ballpark numbers are known. These can be significantly improved by attempting these advanced numerical simulators. Then once we have built a model, then we need to calibrate it with the known data. So porosity can be calibrated, permeability can be calibrated, and better the porosity permeability calibration, better the estimation. So some of these slides I'm going quick for the FYI purpose. And same way, so there are two important parameters: calibration of good porosity and calibration of permeability for the aquifer, and calibration of sealing capacity, because sealing capacity dictates how much column of carbon dioxide can a reservoir can hold. These are by and large known techniques. So what simulator handles is, model handles is structural and stratigraphical trapping mechanism, residual gas trapping, solution trapping, hydrocarbon trapping, mineral trapping. Now adsorption is a separate topic for the coals. So this is the result. So this is run on a demo data in Gippsland Basin, South Australia. What you see here is the total accumulated over a 200-year prediction time, the total storage in free phase, in liquid phase and gas phase, free phase and gas phase simulated outcome. And this is basically high fluid pressure. In the top diagram, you can see that there are zones at 250 megatons are injected over 50 years, there are leakage sites. So these leakage sites can be figured out. That means how much volume a particular site can handle, and at what point the leakage becomes a risk, that can be screened using flow simulations. 50 year and so at 250 megaton injection, 50 year it cannot handle at the two sides, whereas at 100 megaton 50 year, almost all the side looks safe. Now that was the free phase. Now how much of the total carbon dioxide dissolved into the water, that is simulated in this diagram in the basin. So each, wherever you see these dots, these are primarily the sites where either they are closure or there are carbon dioxide injected wells, injection wells. Then the another factor that required to be modeled is aquifer flow. The advection process increases the solubility as well as controls the traffic. So through advection modeling, you can notice that if the aquifer is flowing from 1.5 million year, what are the areas which are become critically or high concentration of carbon dioxide, which are less, and if they're moving from north to the south, the aquifer is from north to the south, then which are the sites. So it is giving not just the storage sites, but potential risky locations where there could be chances of leakage. So both quantification of volume as well as the leakage sites, and this can be modeled for many directions depending on the aquifer location. Then the another tool which is recently added is mineral precipitation into the reservoir. I'm not going into the detail of this, but many carbonate precipitation happens as the carbon dioxide moves, and that's what you see on the right hand side. Those are the blue color, the green color, red colors. They are the zones where the carbon dioxide is actually getting precipitated into the calcium minerals. So that's a secondary storage in a way. Now, so this is a full-fledged, so far I was talking about a full-fledged simulator based modeling. However, we have recently introduced a new technology where the seismic data itself, if the seismic data is inverted or by any method, seismic data is transferred into the rock properties. Once the seismic data is transformed into the rock properties, then using invasion percolation algorithms. So invasion percolation algorithms takes into account the capillarity and buoyancy pressure. These are the two. It doesn't take into account the full physics, but the two critical components of migrations, buoyancy and capillary pressure, are taken into consideration in this model. So you take your seismic tube, convert it into the lithological tube using various techniques, neural network, attributes, so on and so forth, and then inject at the sites. And the simulator can handle the migration of the carbon dioxide as well as conventional hydrocarbon. So it's two-way beneficial, not just for the screening of carbon dioxide sites, but also migration of the conventional hydrocarbons. And that's what you see from the sniper data set on the left hand side. The sites are automatically simulated where the carbon dioxide can migrate to. Yeah, I think this is a video here that shows how in a 3D tube the carbon dioxide is migrated, and then you can hide, so on and so forth. So this is a more quick look, faster method that gives you first hand screening, and then once you've got a good hold on based on this, then the advanced simulation can be attempted. And that's what you see the concentration. The color is basically the concentration of carbon dioxide. Red, the darker colors are higher concentration, and the bluish color are the lighter concentration. The same tool can be used for conventional hydrocarbon migration. Yeah, so that's all I had to show that how a legacy technology of basin modeling is used for more advanced simulation of site selection, and then post that, of course, much more advanced simulators are required before a pilot project or real execution of carbon dioxide into the one. So these risk maps can be built based on these modeled outputs. And the second part is, the first part of screening, second part is storage potential, the actual volume that can be injected using various physics-based models, advection, dissolution, conventional trapping, how much volume can it handle. And then a mass balance can also be calculated. On the right hand side, you can see that it's giving you the overall mass balance, how much is total injected, of that how much is in the free phase accumulated in the basin, at what locations, how much is dissolved into the water, how much is available as a free phase liquid, because a three-dimensional fluid phase, three-dimensional flow simulator. And the locations, the locations where the locations which can handle more storage for how long time with the pressures. Yeah, I think that's all I had to show. And then of course then it can be further enhanced a bit to handle portfolio level assessment. So portfolio level assessment means, for example, it is done for one particular layer, then the same simulation can be run for multiple basins, and the multiple basins, then a portfolio can be run, which storage sites in which basins are the best candidates, and then do the detailed portfolio analysis using advanced static modeling and coupled geomechanic simulators to do the real injection. Yeah, that's it. On the right hand side, portfolio prioritization can be attempted at multi basin level. If it is for one basin, just one IQ4, then a single model is enough. But if it is multiple, then a good portfolio prioritization can be performed. So that's all I had to talk. So in summary, while a gross storage sites are known, well established, published, even public domain, but these volumes can be, these sites screening itself as well as the volume can significantly improved by performing advanced simulators, and which are by and large available in most of the oil and gas industry. They have these softwares. It just need to retune the, use the same model and change the purpose, and then these sites can be better modeled. That's all I had to show. Thank you for your attention, and happy to answer your questions post the after the next speaker.
Thank you, Deepender, for that data-rich presentation. I think that gave us a lot of food for thought. Our next speaker is Mr. Dilip Chauhan from Baker Hughes, who's going to be talking to us about real-time CO2 purity monitoring.
Good afternoon. I am Dilip Singh Chauhan. I am Principal Architect at Baker Hughes. Today I am going to talk about CO2 monitoring. It is an intelligent monitoring, and especially towards the purity and volume of the CO2, right? So I think you guys know in terms of CCUS value chain, right? So you start from capture, transport towards storage and utilization. Okay. Is it better now? Okay. So typically from plants, you're capturing CO2, and then there's a transportation wherein it could be pipeline based or it could be container based where you're shipping it, and then finally you are storing. Of course, there's other options like utilization as well. Right? So now, in terms of current challenge, right? I think everybody wants to kind of decarbonize. All the large companies are going towards the decarbonization, right? And then you are going to capture the carbon from different streams, right? And the different streams sort of giving you different purity, different concentration, different volume, right? And then the challenge comes when you are going to store, and you are going to aggregate all the streams and going to store. And to calculate accurate volume and concentration is a challenge, because if you want to kind of get the carbon credits from regulatories, right, they are expecting certain level of carbon concentration or purity. At the same time, it is also going to impact on your well integrity if you know the phase changes of carbon, right? If there are phase changes in carbon, it may lead to hydrate and then corrosion and then leak and all, right? So that is where I think traditional monitoring is not kind of addressing all these things, right? Because you are not getting a continuous monitoring of this thing. So as a methodology, I mean, this is more from the technical side, like what we are saying is like, I think you are going to receive the carbon from a different sources, right? So I think the first challenge is to kind of grab that data from a different sources, right? So here, I think the sources, your assets could be across your process stack, across your conversion, exhaust or gas treatment, right? And I think that data you can actually connect using industry standard protocol, using Modbus, or I think if the data is stored into any data aggregator like a SCADA also, so you can actually pull using OPC UA or from the historian, right? And then from there, what we do is we actually push that data into digital platform, and that is what we are sort of offering. So digital platform from Baker Hughes side, it's Carbon Edge as a digital platform wherein you can actually push all your data from different discrete data sources, and it could be brownfield wherein your sensor is already installed, and we can actually tap into any data source which is there, pushing it to Carbon Edge boundary. And once we receive that into platform boundary, what we do is we perform certain quality check for sensor drift or missing data and that sort of thing, right? And the same data would be passed to the rule engine to kind of check the envelope boundaries, like in terms of threshold limits and all. If it is actually breaching any threshold limits, we generate the alert and we send real-time alerts using SMS, email, and in system also you can get that information, right? The same data, I think you can visualize in visualization layer, and you can actually get that different stream of data. You can correlate using data fusion, wherein discrete data you can correlate at the real time or near real time, and then you can actually get the historical trend as well. Right? The next, apart from that, we also sort of pass it to analytics engine, right? So analytics engine receive this data and it actually use a weighted average logic wherein it actually get the data from all the different streams and then perform the weighted average logic and then identify the right purity. If it is breaches the certain compliance threshold, it actually generates the alert and alarm. And it's also kind of recommend to the users like what you can do typically in this case, right? So you are receiving the data from different streams, so it can suggest you, like you can actually change the flow from the one wherein we are getting the purest CO2, and then you can manage the threshold limit what is expected, right? So yeah, this is how it actually recommends, and you can meet the regulatory and compliances and without halting your storage operations. Alert I talked about. I think apart from that, I think not just the alert and dashboard, but finally you need this system to be ready for reporting, especially the regulatory and a compliance perspective, right? So this sort of enable kind of generating the reports, data would be ready, and you can utilize that that data, and then you can integrate also. In terms of scalability and integrations, right? You can actually integrate with the carbon credit systems or emission registry system, or in fact in your own digital twin if you have. So this can exchange the data into your digital twin or vice versa, right? So this sort of extendability is what we have as part of systems. Right? We talk about a lot of theory, so this is more in terms of results. So we did one pilot wherein what we did is we sort of pull the data from 5 different emissions sources. It's around 20 sensors, wherein we were receiving high frequency data, sub-second sort of data, and then using our analytics, right, which is sort of performing the average across the purity across the sources, right? So I think we were getting the average effective purity is 91.3. With one deviation wherein at one time it reached to below 90%, which is a compliance threshold. System automatically generated one alert and then share some suggestion or recommendation in terms of what to do next. Right? So, this is more in terms of distribution across your different sources from where you are actually receiving the carbon, right? So it actually helps you to kind of visualize the contribution across the sources and systems. So key takeaway here is it's real-time visualization, which is going to definitely help you to kind of proactively take action on those items. System alert, which actually help you to kind of give you risk information and hazard information, which is connected with the recommendation right? And operation optimization, definitely you don't want to kind of halt your operation just because one place you are actually getting some sort of purity issue. So instead of halting it, you can continuously do operation. So optimization of operation, and then audit ready system is more in terms of reporting, right? So you can get like in US class 6 reporting is there, so you can get all the data which is there, and it is auditable, right? And you can integrate the data into the system, right? And financial impact, I think, as long as if you are going to trace all the purity into system, and you are not compromising with well integrity, right? So definitely there's a benefit in financial. I think the last conclusion is like real-time monitoring is definitely going to improve the reliability and transparency of CCUS operation. And in terms of data, the continuous measuring, audit readiness definitely help you to kind of any sort of reporting, any compliance, any government compliance, and agile, you can actually ready or change the format, whatever is expected there, right? So I think this platform here ensure, make CCUS as a viable solution, of course, because you are going to optimize, and then this is going to help in terms of well integrity and compliance issues. Right? So yeah, that's it. That's what I want to kind of share. Thanks. Thank you.
Thank you, Dilip, for that presentation. I think as the CCTS regime comes up, I think this is something that will become even more relevant. There are a lot of companies in this space that are pioneering solutions. I think Carbon Clean has been one of the early adopters. So our next speaker, Eddie Griffiths, is going to be talking to us about their modular carbon capture solution. Eddie.
Thank you. And thank you to the organizers for the opportunity to speak on behalf of Carbon Clean. I hope you can hear me okay. So I'm going to talk today about how Carbon Clean is aiming to address the challenges of space and cost in carbon capture systems by talking about Cyclone CC. First, a quick introduction to the company. Our experience spans 50 global sites in both biogas and post-combustion capture applications using our proprietary solvent. And we've captured over 2.9 million tons of CO2 to date with our technology. So that's looking to the past, where we also have over 100 active patents in various areas, from solvent to rotating packed beds and other areas. Looking to the future, the right-hand side of the slide, what we're aiming for with Cyclone CC is a 50% reduction in footprint and a 10 times equipment size reduction in carbon capture, along with a reduction in both CapEx and OpEx. Our market focus is post-combustion capture and anything really with a flue gas with 3 to 20% CO2 concentration. Some of the sectors we look at are upstream and midstream, things like gas turbines for data centers. And we also look at other applications such as refining, cement, steel, and the maritime sector, which I'll come on to. So we see really three areas of reducing the cost of carbon capture. One is the CapEx, so the equipment itself. I'll talk about rotating packed beds and how they are tackling CapEx. OpEx, which is really driven by the solvent, and I'll talk about that in the next slide. And the third part is reducing O&M costs through automation and the use of AI. So the first area I'm going to talk about is the OpEx. We're driving down OpEx through the use of our proprietary solvent, which is a patented formulation, and it's a key differentiator for us mainly on the OpEx side of the equation. We've got less corrosion and less degradation than the typical, we use MEA as a comparison because it's the most widely known in the market. And if you look at the right-hand side of the slide, you'll see the comparison in the metal content of the solvent circulating in the system. And over a period of 1,000 operating hours, you can see the color change from the metal concentration increasing in the MEA, whereas the APBS, that's our proprietary solvent, shows very little discoloration in that time. That contributes to a longer solvent life and a lower makeup rate, thereby lowering the OpEx. Other areas, of course, we know that the thermal demand, the heating capacity, sometimes called the specific reboiler duty, That's a key cost for carbon capture. So we've got a lower energy demand from this solvent formulation, and also lower emissions, which also reduces solvent makeup rate. So that's on the OPEX side. On the CAPEX side, we're looking at the equipment for carbon capture. This is traditionally done in large packed bed columns, static packed bed columns. The innovation we're bringing to carbon capture is the rotating packed bed, where a structured packing is a donut of structured packing is spun on its axis at hundreds of RPM typically, and that stretches the solvent into a thinner film. And that thinner liquid film gives you a much larger surface area for mass transfer of CO2 from the flue gas into the solvent. So I'm just going to hopefully replay that video. I hope I don't give you seasickness, but we'll try and get there. Right. So in the rotating packed bed, we inject the solvent at the center of the packing, and then the centrifugal force from the spinning of the packing stretches that solvent into a thin liquid film, and it travels to the outside. Here it's now rich solvent with CO2 in it, and it drains away over to the stripper. And then the gas coming in purple is given a little push by a blower in the system, and the gas goes through the packed bed in countercurrent flow. Countercurrent flow like you would have in a column, except here we've got a much shorter residence time because we've created that higher surface area for mass transfer. So that's the principle of the rotating packed bed. A little bit about our history in rotating packed bed development. You might have seen in marketing materials from the past the 1 ton per day rotor, which is a 1 ton per day RPB on the left of the slide. We tested that starting in 2021. By 2023, we designed and built a 10 ton per day system. I'll show that on later slides. And now we've scaled up further through 2024 to what we call C1, which is up to 285 tons per day. So that's 100,000 tons a year if you prefer that unit of measurement. That's C1. We designed and built that so that we could put it through its paces in factory acceptance testing. And you see it hooked up here with ducting and with a liquid circuit so we could test the hydraulics of the system and run water and air through it. So the process itself, it looks a lot like a regular amine-based carbon capture system, but each of the packed bed operations you see in a traditional system is replaced with a rotating packed bed to miniaturize or intensify the system. So we've got much experience, which I talked about on earlier slides, in operating these plants with conventional columns. But you see here the pre-treatment section, which is now an RPB, 2 stages of absorbers, which are also RPBs, and finally the water wash. Sorry, not finally. Finally would be the desorber, which is the stripping operation to strip the CO2 from the solvent. So our experience so far with Cyclone CC goes as far as this nominal 10 ton per day demonstration unit, which has been deployed in 2024 at Fertiglobe site. That's a wholly owned ADNOC subsidiary in the Middle East. And is currently in operation at a Saudi Aramco site in Saudi Arabia. The first source is a kind of what we would term a medium concentration flue gas, so in the region of 8 to 10%. And the gas turbine is a very low concentration, around 3 to 3.5% CO2. So it's a greater challenge for the system. This video shows the deployment of the system and really speaks to the value proposition around Cyclone CC. What we believe in is fully modular, prefabricated systems, reducing the amount of site installation time, reducing the site installation cost, which is the one that tends to be the highest cost and the lowest productivity. So what you see here is in 4 days, we assembled the system at site. Within 1 week, we were fully mechanically complete, and within 3 weeks, ready for commissioning and startup. So that's the kind of the value proposition in a nutshell when it comes to CapEx, which is the total installed cost being reduced. So what did we achieve? We set out obviously a set of KPIs with the customer, and we wanted to achieve over 90% recovery. We did that, and based on an 8% CO2 concentration, the system was designed for 10. We wanted to capture 8 tons per day. So we captured our 8 ton per day target. And the captured CO2 was used directly in the urea production process on the site, achieving great product purity. Steam demand and power demand were lower than the targets. And I think one of the big questions I always get about Cyclone CC is about reliability. So I'm really pleased to say in around 4,000 hours of operation, we had no shutdowns that were attributable to the RPB. So the RPB was remarkably reliable, or all three of them, for the duration of the test. So beyond that, I talked very briefly about C1. So C1 is our product for up to 100,000 tons per year, or 285 tons per day capture. And here we're demonstrating the smaller footprint of an RPB-based system and full modularization. We plan to offer this we offer this as standardized and scalable designs. And what does that mean in reality? So what you have on the left of this slide is a typical absorber column of 30 meters in height. That's not including the water wash. And in comparison, the RPB is around 3.5 meters width and height. That means that it can be road trucked, standard road truckable dimensions, unlike a column which would require special transportation and route planning and so on. And it reduces the total steel requirement in the plant by around about 35%. And in terms of weight, particularly important in a maritime environment, we move from a system where we've got around 500 tons in weight of columns and packing to a saving of around 65% on the weight in the mass transfer equipment itself. Just mentioning maritime, so we see particular advantages of the RPB system for onboard systems, and that's because as well as the height, the weight, and the size of the equipment, we also see an advantage to moving from relying totally on gravity, where you have a section of the column that is not being properly utilized because of the motion of the ship. Whereas in Cyclone CC with the RPB, you get a good distribution of liquid and gas no matter what orientation of the RPB itself. And finally, I wanted to speak to our presence in India, because we're very proud of our Indian roots. Carbon Clean was formed as a company in 2009 in India. We're currently headquartered in London in the UK. Our co-founders, Anirudh and Pratik, work out of our London office. But last year we were very pleased to about the inauguration of our Global Innovation Center, which is in Navi Mumbai. And we plan for up to 350 employees there. And just I'll quickly talk about the capabilities we've now got in-house. So in-house, we've got a process development, solvent development lab in-house, an analytical laboratory, which gives us the ability to support after-sale service and so on. And we've got a 2-ton per day pilot plant within our own facility, which we can run with both conventional columns and with RPBs. And we got all of the capabilities on site to go from TRL1 through to TRL7. So that was it. Thank you very much for your time and attention. Please do come and find me after the session if you've got questions. I'm in Hall 2 on the UK Pavilion. So thank you.
Thank you, Eddie, for that presentation. And I think the videos were certainly very helpful. Our last speaker is Ayushi Gupta, who's going to be talking to us about design considerations for pipelines, given we have a lot of corrosion and other issues that we face. So Ayushi, over to you.
Good afternoon, everyone. I am Ayushi Gupta, production engineer from ONGC, from Pipeline Group of ONGC Mumbai. I'm very happy and elated to speak at India Energy Week 2026. So my topic is carbon capture and storage, CCS, infrastructure and design considerations for CO2 pipelines. So India has set an ambitious direction with net zero by 2070, and one message is clear: capturing CO2 is only half the job. Other half is moving it safely, reliably, and at scale. So today, I will focus on the backbone of the CCS deployment, that is CO2 pipelines, the infrastructure choices, and the design considerations that decide whether CCS remains a pilot or becomes a national scale solution. So I wanted to start with this image because it reminds us that climate change is not just about numbers and graph. It's actually happening. There are many things we are actually losing. So in 2019, Iceland held a funeral for a glacier. If a country can lose a glacier in one lifetime, it tells us how fast the climate is changing. So for us in India, we may not see glaciers every day, but we do see heavy rainfalls, extreme temperatures, floods, everything happening. So the question is, how do we continue to grow as a country and still reduce the emissions that are driving this change? So my agenda is to discuss first the India net zero commitment of 2070, then ONGC vision of 2038, then why we need CO2 pipelines, then a basic CO2 pipeline infrastructure, then the thermodynamic behavior of CO2 in pipeline transportation, material selection and corrosion challenges, what could be the potential storage sites for CO2 in India, and the proposed layout for India's CO2 pipeline infrastructure. And as we have many oil and gas industries, so we are already having natural gas pipelines. So how can we repurpose those natural gas pipelines for CO2? And then the route planning in high density regions, policy and regulatory needs for CCS, ending with the conclusion and references. As announced by our Honorable Prime Minister Narendra Modi at Conference of Parties 2021 at Glasgow, he took Panchamrit climate pledges. So the first was India will take its non-fossil energy capacity to 500 gigawatt by 2030. Second, India will meet 50% of its energy requirement from renewable by 2030. Third was India will reduce the total projected carbon emissions by 1 billion tons. And fourth is India will reduce the carbon intensity of its economy by more than 45%. And the fifth was by 2070, India will achieve the target of net zero. So India's message is clear. We will grow and decarbonize at the same time. And in that journey, technologies like CCUS and CO2 pipelines will be very important, especially for the hard-to-abate sectors. In line with the India's Net Zero 2070, our ONGC has a vision of 2038 strategy for achieving net zero operational emissions, Scope 1 and Scope 2 by 2038. So Scope 1 is the direct emissions that the sources we own or control, that is ONGC turbines, boilers, flares, company vehicles, etc. And the Scope 2 are the indirect emissions that are from electricity, steam, heat that we buy, that is grid power used in ONGC offices. And ONGC has multiple decarbonization levers. There are many mitigation measures like renewables, solar, onshore wind, green hydrogen, biogas, offshore wind, CCUS, and they are investing approx 2 lakh crores for the ONGC vision of 2038. And for alone CCUS, it's around 2,000 crores. So the ONGC vision is very much aligned with the India's net zero commitment of 2070. So now coming to the CO2 pipelines. So as India is committed for net zero 2070, sectors like steel, cement, refineries and fertilizers will eventually need to capture and move large amount of CO2 to storage sites. That means in the long run, India will need something like a CO2 pipeline network. So just like we have a natural gas grid today, since ONGC and other PSUs and other private players have strong experience in oil and gas pipelines, so I felt it is natural to ask how can we extend this expertise to CO2. So in this paper, we have tried to look at the future design questions for India, what state of CO2 should be transported in, how its thermodynamics, materials and corrosion behave, where pipelines might go, and whether some existing gas pipeline can be repurposed. So the idea is not that this is going to be built tomorrow, but to present a futuristic yet realistic roadmap of how India could plan CO2 pipeline infrastructure to support both climate goals and industrial growth. This is a basic CO2 pipeline infrastructure. CO2 is captured from the industrial plants and then it is being sent by pipeline to storage sites. And wells are through the pipelines, they are being injected into the depleted oil fields and saline formations, and then Caprock seals it and keep the CO2 trapped. At the same time, we can use this CO2 for enhanced oil recovery to push out. But the real CO2, they have impurities like H2O, SO2, nitrogen, etc. So these impurities can shift the phase boundaries. And then they can also affect the pressure drop prediction and increase the fracture risk. So during leaks, strong cooling can cause this two-phase or dry ice. So cooling plus impurities can create the corrosion hotspots and threaten the integrity. So the key message is in CO2 pipelines, thermodynamics, corrosion control must be managed together to ensure long-term integrity of the pipelines. Now, the material selection and challenges. CO2 pipeline life depends on both the material and the gas quality. It's just not the hydraulics. So as per the studies, carbon manganese steel works well in the dry, pure CO2. So, but in the real case scenario, impurities and water are present, which is going to produce acids and it is going to have corrosion in the pipeline. So flowing conditions, real flowing conditions can make the corrosion worse and continuous. So we need very dry CO2, low water, and we need strict limits on the acid forming impurities. If impurities cannot be fully removed, then we can use coatings, inhibitors, corrosion resistant alloys, and plus monitoring which is suited for the CO2. For India, impurity-rich flue gases mean strong national standards are critical. So we need to require a national standards so that all the industries can maintain the same standards. For this, we have suggested a hub and cluster model. So India's, as per studies, it was found India's emissions are concentrated, 60% of CO2 comes from 64 districts. So this favors a hub and cluster model. So in this, so like we have various industries like steel plant, hydrogen, cement, and fertilizer, which are concentrated in an area. So where so they can share a trunk line like CO2 collection hub, and this can be transported to either offshore storage sites or the onshore storage sites. And this cluster should be defined by proximity of emitters like power plants and cement kilns, steel facilities, refineries which are within 50 to 100 kilometer radii. So now India has two huge candidate potential storage sites for CO2 in India. First is Cambay Basin, that is in Gujarat. So the thick sediments and the depleted oil and gas fields for CO2 storage. So they support the saline aquifers and the EOR opportunities. And the basin has good porosity, permeability, and strong cap rock. And it is very close to the major emitters like Ahmedabad, Vadodara, Ankleshwar belt. And as we have already oil and gas subsurface data, so we can use the same subsurface data for the storing of CO2. And it is a strong candidate for India's first CO2 corridor. The second one is the Deccan Traps, which is along the length of Maharashtra and Madhya Pradesh belt. So there is the basalt formation, which enables mineral carbonation. So there CO2 will react with the carbonates and it will form calcium carbonate. And so it becomes a solid rock. It's a proven fast mineralization option, and it is spread across Pune, Mumbai industrial belt, and and it's a very high term security because it is going to do the permanent wrapping of the CO2. So in line with this, we have proposed a layout for India's CO2 pipeline infrastructure that is divided in 5 corridors. So the western corridor, which we just talked about, that is the Ahmedabad, Vadodara, Ankleshwar industrial belt. So the storage for this belt, the storage will be in the Cambay Basin, the saline aquifers and the depleted fields. And that is the shortest sourcing distance in India, and it's a strong candidate for demonstration projects. The second is the eastern corridor, that is the Jharkhand, Odisha, Chhattisgarh steel and power cluster, that is in Bokaro, Rourkela and Angul. And for this storage is Mahanadi and Bengal basins, sedimentary, with potential extension to offshore of Bay of Bengal, and like concentrated heavy industry trunk lines can follow the existing rail utility corridors to minimize the land conflicts. The third proposed is the southern corridor, that is near the Chennai industrial region and the coastal power plants in Tamil Nadu and Andhra Pradesh. And the storage site for this is Krishna Godavari Basin. It's onshore plus offshore. So for this, a direct connection between coastal emitters and prolific storage basins, and there are opportunities for offshore pipelines. The fourth one is the Deccan corridor that we just discussed, that the Pune-Mumbai industrial region, Maharashtra power plants, and the storage is in the Deccan Traps. So it's suitable for the pilot projects of mineralization-based storage, complementing saline aquifer pathways. And the last one is the northern corridor, that is the Delhi NCR and the surrounding cement power clusters. And the storage requires long distance trunk line that would be going to the Cambay Basin. But since the demand is high, but storage options are distant, so we can take this candidate at a later phases once the national backbone matures. So this is being depicted in the map. So this Delhi, NCR and Ahmedabad belt is going to the Cambay Basin, Pune, Mumbai Deccan Traps, Chennai to KG Basin, and the Jharkhand Odisha belt to the Mahanadi Basin. So now the next thing is how can we repurpose the natural gas pipelines for CO2 transport. So India gas pipeline can reduce costs and time for early CCS projects, and because we are already having the right of ways, and it can avoid delays in acquiring the new corridors. But CO2 behaves very differently from natural gas because it has higher density, rapid cooling, different decompression. So many, maybe like old pipelines may not have the enough fracture toughness for dense phase CO2. Therefore, pipelines cannot be just switched, they need requalification and retrofitting. So what are the steps for repurposing these pipelines? First is the integrity audit, that is the pigging, corrosion checks and weld quality. Next is fracture toughness, then checking the coating corrosion assessment, then doing the gas treatment check, hydraulic recalibration, monitoring upgrades, and then the operating training for the regulatory approval that comes under the CCS codes. So the next question is the route planning in the high density regions. So the best routed can be along the existing corridors, that is roads, rails, utilities, and we can use the GIS based planning population, that is GIS planning for this. The policy and regulatory needs for CCS, we need a dedicated CO2 Indian standards, and we can have this specific pipeline design and operation codes aligned with the DNB codes and the ISO codes. And we need a common career model so multiple emitters can share the trunk lines, and we need financial incentives like tax credit, carbon pricing to attract investments. So the conclusion is, to sum up, India can start CCS with few smart, short CO2 corridors linked to secure storage, and then scale outwards as shown. And then from an engineering point of view, three things are non-negotiable: dense phase CO2 with strict impurity control to keep the flow stable and avoid corrosion, verified material integrity and fracture toughness, and careful routing in high density regions following the existing corridors. So the real challenges and the opportunities to put in place the regulatory certainty, financing mechanism, and public trust that will allow CO2 pipelines to grow into a true backbone of India's net zero strategy. These are the references of the paper. Thank you. If you have any question, you can mail me, or you can scan the QR code for the LinkedIn profile. Thank you very much.
So thank you all for taking the time to come listen to all the eminent speakers here. I think very interesting discussions, and going forward, we will see a lot of action on the CCUS front in India. So thank you all for your time.